weather. It's nice. I've been studying outside all day.
Oh, yes. Yes, yes. I hope that stays temperate. Yeah, I think we're going to get a little bit of a cool spell here before we reach a newer steady state. That's actually very nice. You like to go out on the study?
It's in between, like, the resource center and then, like, the chemistry building. There's, like, the 3 trees and the 2 benches and, like, a couple circle tables or square tables. That's where I've been sitting.
Okay, awesome, awesome. Anything else going on that's pleasant or not so pleasant? How about this course? How are we doing? Questions administratively? Oh, yes. So we'll talk a little bit about the projects, okay, the outlines right now. At this point, most everybody is in a group of 3. And there are a few that seem to think are looking for group members. I hope they are. I sent them a message today. So they, and there was one group of 2. If there are others that I don't know about at this point, please send me a message in the Canvas box. I went through the submissions for the pre-proposal, and I was able to get some information. That said, I'm not getting all the information. So if you're having issues finding group members, just let me know. Okay, so after spring break, we'll have our next checkpoint for the final projects due Monday that we get back. So I think that is 23rd or so. And so that's posted. And that's the first assignment where you're going to be using the template that I posted. And just one of the 3 of you will put it in your shared folder. And that link should be the same essentially for the rest of the submissions of the semester. Okay. And it has a lot of sections in it. Okay. And so for the preliminary outline, you're not expected to answer all the questions in those sections, and I specify which ones you should or you should not in the submission. I do want to kind of give a little bit of an overview though for the entire paper. Until you submit the final report, I'd appreciate if you kept it in outline format. So one thing is, please don't remove bullets until, that was wild. It just like, didn't do anything. Okay, I don't know why I did that. Until we submit the final report. Okay. So if you read, or not, well, you could read, there's How to Write a Paper by George Whiteside, there's a link to that. If you watch the videos, we're going to attempt to follow the outline format until it's time for the final manuscript, per se. That doesn't mean you can't have sentences and you can't have figures. You better have figures, you better have sentences in the bullet points. Just that we're going to keep it in outline format until the very end. And in the very end, you'll still have an abstract section. You'll still have an introduction section. You'll still have a methods or an experimental design section. You'll still have a results and discussion, conclusions, and references. All those main sections will be in your final report. It's just that the individual bullets, like you can take out content, what do we do, let's go ahead and we'll just kind of walk through these different sections. In the abstract, there are kind of 4 bullet points that you want to have addressed. And you're going to be somewhat repetitive, okay? Because the abstract is supposed to be this overarching summary of what you done. And you may not write the abstract until a little bit later, okay? But we want to be thinking about what is it that we did, and that content, you can put it in a sentence or two. It doesn't have to be that long. We studied the effect of frontal cross-section area on the effect on the measured drag about an object in a 2D transient or steady state, whatever simulation. So you can be very specific about what you did in that content. So this is where you can, even though it's only a sentence, be specific. Okay? Now, you might ask, what's the difference between the objective and the context? Well, the objective is kind of this higher ideal that you're trying to solve some type of academic problem. So instead of being very specific, this paper describes the relationship between the coefficient of drag and frontal profile in a 2D axisymmetric geometry. That would be your content. The objective would be, we're attempting to understand. So this is more where you say understand. Okay, right? Understand. This is like higher level science. Right? Broadly speaking, we're attempting to understand how drag affects the energy efficiency of automobiles. Okay? And so trying to, and you know, so you can go into how that would be related, of course, to the amount of drag that you have. And the most important results, then you can, most important results, you go this, you refer back to the content. Okay? And, you know, maybe one of those results is a surprise that when I put a headlight on this automobile, the drag coefficient went down. I don't know, okay? Just like something like, you know, a surprise, okay? But that's where you get an or, you know, we found that, as you would expect, you don't necessarily as you would expect, but that the cross-sectional, frontal cross-sectional area is reduced, the wetted area is reduced, the lift, the coefficient of drag goes down, or maybe the coefficient of lift goes up, or the ratio of lift to drag goes up. And then who cares? This is kind of where you talk about the societal issues. Okay, so why does society care? Okay, and you can say, you know, we are in the middle of a growing population or something like that, and we have trying to harvest more energy from the resources that we have at hand. Okay, something along those lines. And so this study would affect decision making along those lines. Okay. Now, in the introduction, what is the problem we are trying to solve? What is new? So that's a little bit of a combo of our objective and our content, right? So here, you can be pretty specific. You can be pretty specific about the problem, okay? And you can also kind of allude to what is new, allude to context. So you're going to allude to the context of essentially engineering and scientific literature. Okay. So here, what I would like you to do is essentially talk about so-and-so did this, so-and-so. Well, I mean, that's actually more in the background, okay, where you put the list, you have like your background references. But you might say, you know, someone has done this. Or you might even say, I mean, give credit where credit is due. We found this tutorial in ANSYS that addressed this problem. That said, we went a little bit further. They did not address this is where you're going to talk a little bit about what's new. Content is going to be repetitive, what you kind of did before, and your motivation. That could be about who cares, or it could be about a scientific problem. So we don't really understand the effect of turbulence on this particular experiment. There's one thing that's missing, though, from all these topics and in the introduction, and that is hypothesis. So at some point in your introduction, I do want you to explicitly state what your hypothesis is. And so there is where you're going to put forth that depends on okay? Or another way to phrase hypothesis is if we have then okay? In the end, when you conclude and then when you discuss, you're going to suggest whether your data support or reject your hypothesis. So you remember, we can't prove a hypothesis with one study, okay? But we can essentially disprove a hypothesis with one study. We can hope if it's a good, good hypothesis could be disproved or supported, right? Ideally, right, you're supporting your hypothesis, but maybe you have an unexpected surprise. Maybe you're going to learn something. I'm not going to penalize you also if you change your hypothesis as you progress through the semester. All right. So that's the introduction. The methods or experimental design. You're going to put forth the kind of areas or the tools you're using, okay, or the principles you're using, and you can already see in the template that I provided that it's like, okay, you can add as many sections as you like, or the different tools or techniques. Okay. And then in the results and discussion, this discussion is going to be the largest weighted single section, or the results of this section will be the largest, combined weighted section of the final paper. And I'll distribute the rubric that we have for that distribution as well. So, and that's based on Professor Singer's desire for us to make sense of what we have produced. So you got to go beyond just pasting a bunch of figures in form. I want us to be customers to understand the exact. And conclusions, okay, you're going to summarize what you have, and then in references, how many references do you think you should have? And what types of references should you have? Maybe that's an easier question. So where are you going to get your references? What are you going to be citing? Yes? Sure.
Like paper, maybe.
Yeah, right. So it's mine, right? Yeah. So you're going to be looking at academic articles. Okay, so at least 3. Okay, and then overall, you need to have at least 5. Okay. And they need to be real references. 5 years ago, it wasn't even an issue of these hallucinated references. Okay? But they need to be real. Okay? So please, and then use them. They'll help you. Okay? Put the tutorials, whatever you're using, put in the tutorials. Right? There are these. I can already see some familiar themes, all right, coming up in the submissions that you have, right? Put in the references, put in the tutorials that you're using, the YouTube videos, if you will, okay? You wouldn't necessarily do that in an academic article, but it's very appropriate. And there's no way you know this. There's no way you would know this, or that you did this. That's not gonna go well, okay? So please cite, please cite. Any questions? Comments? Okay. So, logistically, what you should see is that you can now put your team, or you can put yourself in a group, okay? That's like final project group 1 to 72 or something like that, okay? So, agree with your group members and end up in that same project group, and that in the assignment that you're going to be submitting will be a group assignment. Okay? So let me know if it's not working properly. But this, the preliminary outline and the demo simulation are now up. Those assignments are, and they should be associated with a group that you have. And that way you'll be submitting one response. Except everyone needs to submit surveys. Okay? Everyone needs to submit a survey. Any questions? Okay. Let's talk about fluid mechanics. So, what happens when you're walking along and there's a puddle on the ground and you slip? You fall. Okay, yes, that's the mechanical response. Who said that? All right, thank you. Yes, you fall. Okay. What is happening at the interface? So we have the ground. And we have your foot. Okay. We'll call this your foot. Okay. And your foot is got some velocity. What's in between these two plates? Well, we could say we have a nice little, I guess I'm using my blue, but we have a nice little bit of fluid in between them. Okay. What do you say for the boundary condition between the ground and the fluid and the foot or the shoe? What is the boundary condition that you all remember from fluid mechanics? Huh?
Distance or thickness?
No, boundary condition. So this is the boundary condition. So yes, there is, fine. We can say there's a gap. That's fine. There is a gap. We'll call it H. But what is, yes?
No slip.
No slip. But you just slipped. How is that possible?
Boundary layer.
Okay, oh man. Okay, well, we're getting right into the jargon. All right. So, well, if there's no slip at the top and no slip at the bottom, what's going on? Yes.
No slip describes how the fluid acts in contact with the surface.
Right, so right at the surfaces, right, we say no slip to describe the velocity of the fluid. Okay? So, and it's not slipping, so that means that what's the velocity of the fluid? So if the foot is slipping at V naught, what is the velocity of the fluid particle right next to the wall up there? Also V naught, right? It's not slipping, right? Okay, good. Okay, so, and then if this is ground, right, the fluid particles right next to the ground are at zero velocity, right? Because they are also not slipping. Now, that means that if I think about the profile of velocity, it looks something like this, right? I have a V naught here and I have 0 here. Now, if I want, let's say this, okay, so it's doing this thing, right? And what is the variable that we often use for fluid velocity? Well, today we're going to use lowercase u. So if I want to, so my boundary conditions, right? If I want to describe my boundary conditions, I'm going to say that the coordinate system is something like this, x and y, like that. And this is a fully developed flow, right, whatever, you know, and it's moving along. What we can say is that u of y equals h is going to be v naught, right? And u of y equals 0 is going to be equal to 0. And these are the no-slip conditions. Now, you already see on the left side, right? This bit for laminar flow, incompressible isotropic case. What is the shear stress? So if I have a little element, okay, right there. So my little element what is the shear stress going to be on this fluid element, just in terms of arrows? Maybe think, and let's say that this element, it's a function, because it's fully developed, right? It's not going to make a difference where it is in the x direction, but it's going to make a difference. Well, maybe it doesn't make a difference though, actually in the y, right? But let's say that I'm moving it up to the top here. The velocity, right, is going in the right direction. So what do you think, which direction? I'm talking, okay, I want the state of shear stress, right? So we want the state of shear stress. Sure, I don't know which color. We'll use blue again. Okay, what is the state of, what does it look like? Just arrows, no equation. But what does it look like? Yes.
Would be an arrow going to the right at the top and then an arrow going to the bottom.
Yes, okay. So that's good. All right. And what are we going to say for the magnitude of the shear stress? Now, what are we going to call it? Well, we have an equation right there, correct? This mu du dy, right? And what do you think the viscosity, or what do you, okay, so first of all, this is dynamic viscosity, right? So the dynamic viscosity has units of, well, some units we use are Pascal seconds. What is this as du dy. So u is velocity in x direction, okay, and y is, well, the vertical direction. So what would it be? What's the derivative of the u with respect to y? Quadrant 4, you've been climbing kind of quiet. Alright? What do you all think? What's the du dy? Sure, stop.
0?
Well, okay, so let's think about it. Is u changing as you go upward? Yes. Okay. So does that mean that it's 0? No. Okay. So now what do you think it is?
The derivative of u.
It's the derivative of u with respect to y. Awesome. Okay. That is a. Is it a straight line? Well, okay. Is the profile of u a straight line? It is actually. It's got a slope to it. Okay. And what is that slope? How do you think you could think of it? Now, it might be sideways, but slope is rise over run, right? So what's the change in velocity over the entire gap? Okay. Yes, it's a change in u. Okay, yeah, go ahead.
It's V naught times y over h.
Okay, right. So the slope, this is just the slope, okay? So V naught over the entire h, right? So we'll just say that the du dy is V naught over h. Okay? So yes, if you want to know u, you have to integrate that and then you multiply by the y. Okay? This is what you suggest. Okay. Good. All right, now, if I am thinking about dv dx, okay, so now v is velocity in the vertical direction. As a function of x. So maybe we can do another thought experiment. We said there's a no slip condition at the bottom, okay? And yes, that usually refers to the tangential component. But is there any velocity in the vertical direction? No, right? And if I get to the top, is there any velocity in the vertical direction? If I get to the middle, is there any velocity in the vertical direction? No, there's no velocity in the vertical direction, right? So if I take the dv dx component, this is 0. And this is annoying, right? Because in solid mechanics, you've got to have the balance, right? All your shear stresses have to be the same on all the sides. But this is a Newtonian fluid. This is a Newtonian a problem on viscosity. So we're not doing a problem on elasticity. Okay? So we're content with just having these shear stresses on the top and the bottom of the fluid. Right? Because you remember, you can go back to your mechanics, you can be like, oh yeah, that's the top side, right? Such y positive, you remember this? And it's in the x direction, right? So that's like that's going to be your that'd be your essentially your tau yx. Okay. Now, and then this would be your tau now negative y, negative x, right? Those are the same. So those balance each other. Okay? But we had to be a little bit careful, right? And when we think about what's happening on the x space in the y direction, okay, and on the negative x space, the negative y direction. Anyway, you're like, you can already tell yourselves, I know I don't need to know this to do answers, right? Okay? We're just trying to remind us a little bit about what's happening in fluid mechanics. And so if you're looking at the total component though, okay, this tau xy or tau yx, it is defined in the 2D case, the general 2D case, as having both of these components, right? And what we just said in our previous example, right, was that this was the V naught over H, right? And this one was equal to 0. But of course, you can find systems where it is not the case. In 3D, then what you have to concern yourself with is that you have a tau xz, right, and a tau. So if you're doing tau xz, right, you have to look at the derivative of the x with respect to z, and then you have the w, that would be the velocity. Okay, I'm sorry. So tau xz, you have to look at the du dz plus the dw dx. Okay, and that way you could have these pairs that you line up with each other. Okay, because essentially you're looking at two problems. Now, one thing that we kind of skipped, is that really du dy dv dx, or this idea of du dy, right, and then the dv dy, dz, the dw dz, right? These are really gradients that we're taking, okay? And so the shear stress that you have is going to be dependent on the gradient. And also a gradient of the transpose, okay, of the velocity. So, if you want to have fun on a Friday night, and hopefully this Friday night you get to at least take a little bit of a breather, spring break is coming, you could watch some of these great videos by the Efficient Engineer. Okay, one's on viscosity, and the other one I have for you is on laminar and turbulent flow. Okay. Now, for laminar and turbulent flow, what is your go-to number? The Reynolds number. Okay. So let's just say that you have a pipe. Okay. A pipe, all right, and it looks something like this. It's so beautiful, okay. It's going along. That's really ugly, actually. And you've got, some diameter, or maybe a radius. So let's just say radius diameter. And this liquid has some viscosity to it. And it's got some type of velocity, right? What is the Reynolds number here? Anyone? Okay, quadrant 1. What do you think? Someone in quadrant 1. I guess I can give it some density too. It's got a viscosity and it's got a density. Okay. Now is it complete? Okay, Zachary, what do you say?
Times the density of the fluid times whatever velocity it's moving at times the length of the
This is where it gets good. This is the length. So if you have like flow over a plate and you're doing like the glossius, you guys covered that, right? The boundary layer. Someone said boundary. Who's boundary layer person over here? All right, yeah. So now you say, okay, boundary layer. I wrote VL, but this is a pipe, right? So usually in pipes we use diameter. Okay. So rho V D. Okay, and then yeah, we divide by the diameter. Okay. So what are the different regimes for your flow, right? You just saw, we said, oh, there's turbulent and laminar. Okay. So usually you have some type of, you have a laminar regime where everything is awesome. Actually, we'll even do nicer. Okay. You've got the transition, and then you've got turbulence. Right? And in turbulence, everything is chaotic and it's a pain. Okay? And if you've got your boundary layer problem, you know that, okay, is the boundary can become be nice and laminar, and then when you get farther away, then that's when it gets chaotic and turbulent. Okay? What are the general numbers that you use to describe these? Yes. Okay, yeah, so good. So let's just say, yeah, you said 2300, 2400, something like that, right? 2000, okay? And then over here, yeah, you could say over 4000, that's fine, that's safe. And then between this transition. And if you have like a nice smooth surface and you don't sneeze on your experiment, you can get it to stay laminar for a little bit longer. But if you have any perturbations, bubbles or whatever, surface roughness, it could get a little swirly. Okay. What types of problems do you think we're going to do in this class? What do you think ANSYS can do? Yes.
Probably laminar, maybe transition a little bit, but.
We're going to do them all. All right. It's going to be fun. Okay. So we're going to talk a little bit about turbulence. In order to get good, I don't like using good. Right? That's too subjective. We're scientists, we're engineers, right? In order to have accurate measurements for the coefficient of lift and drag, you've got to account for, on airflows in particular, you have to account for turbulence. Because those Reynolds numbers are typically pretty high. And even in the lab that we're going to do on Thursday, we go ahead and implement one of the turbulent models. And you can see some nice little slopes. Okay? But we're going to have problems that are in all these regimes. And there are tricks that people play to get a model that is pretty accurate for these chaotic flows. One of our seminar speakers, though, recently reminded me that you should tell the students garbage in, garbage out. So we have a couple of phrases in this class. One is baby steps. Okay. That means that you try to do the simplest problem you can, that you can solve analytically, or you have ground truth, and then you go extend it. 2, the experiment always wins. Okay? Which is kind of sad in the simulation class, but it's true. So that goes to a baby step. So if you have experimental data that you can compare to, that's very nice. And then maybe the third one could be garbage in, garbage out. Okay? 3 cliches for your data. So if your model is not very good, or you get boundary conditions wrong, or lots of pretty pictures, but you just may not be simulating anything that's meaningful. For your enjoyment, we're going to review the derivation of Navier-Stokes equation. Okay? But we're not, do you want me to, should we just write them all out together? Would that be fun?
So much fun.
So much fun. No, we're not going to do that. So you can put your pencils down. I might give you already asleep, but anyway. You can put your pencils down and just have this reminiscent, nostalgic feel for the Navier-Stokes equation. Okay? So, we start with a velocity field. No. Okay, sorry, I made a mistake here. Okay, yeah, this, and I'm going to double check, but I'm going to go ahead and put these arrows here, all right? Because that's still tau x, y, and tau y x. It's still true that d dx is equal to 0, okay? But there's no contribution to the shear stress from the v term. Okay, but let's go ahead. Sorry about that. Okay. It's just looking, just reminiscing on Navier-Stokes reminded me that I made a mistake. Okay, so here we go. You have a velocity field, okay, in Cartesian coordinates, and you have a u of x, y, z, t. You have a v of x, y, z, t. And you have a w of x, y, z, t. You can take what we could call a total or material derivative. That's the big dv dt that you see there. Oops, now you don't see it anymore. Okay, and then what you get is this expression, which looks kind of like a gradient. Okay, but we had to use the chain rule to break down what you have happening in these u's of v's and w's. The u's of v's and w's, they have a time dependent component and they have a spatial component. So if you use the chain rule like you see here, we can write out this expression, and now you have a partial of u, and this is just for the u, right? So we're taking this one. You have to do the same thing for v, you have to do the same thing for w. Okay? So we can take this expression, all right, and we can go ahead and write out what the component for the du with respect to t is here. We end up with this divergence operator, okay, and then we can multiply that against u. We are going to have, for each one of these velocity components, the u, the v, and the w, okay, that you have here, okay, that you're going to have these set of equations. As you remember, Cartesian coordinates, Navier-Stokes equations, usually write 3 lines. Okay, now, we have essentially just gone full circle and written this out again. And we can now look at this acceleration term, not with just the u, but in terms of the v, the overall v that you have there. And as we said, we have this total derivative. Those are differential relationships for particle. Now, let's look at mass conservation, right? So with mass conservation, you have some type of flow into an inlet and some type of flow out, okay? And if we're conserving mass, which we're doing in most problems, okay? And that would suggest that we have a density, we have a velocity. We can integrate these expressions, and we can also discretize these expressions, and this will become pretty relevant and something we discuss later, the numerical method that we're going to be Now, when you do this all out, okay, what we get is this expression, and if the density is not changing as a function of time, we have this divergence, okay, of the velocity, okay, is got to be equal to 0. And we can factor out the rho, and so we're just left with the divergence of velocity is going to be equal to 0. And that's what you have here. That's the continuity or conservation of mass. Now, we can go a little bit further, and we can remember that if you have an inlet and an outlet, like a nozzle, density not changing, you can also say you have conservation of volume. So, for example, in this case, I can say that V1A1 on the inlet is going to be equal to V2A2 on the outlet. Momentum comes into play, and momentum is saying, hey, let's sum the forces on these different sides of this element. And when we do that, okay, we can say, oh, there's some stress on this side, there's some stress on this side, there's a difference of a dx, there's a difference of a dy on a 2D element, and we can say, okay, that sigma x times that cross-sectional area is going to be some force, that sigma x on the other side times that cross-sectional area is going to be some force. I'm going to say, okay, there's going to be some type of balance. Balance in the two forces. Happy are we that this is not a mechanics problem, because if it were a mechanics problem, solid mechanics problem, this is fluid mechanics. If it were a solid mechanics problem, we would also have to keep track of the moments. But we don't have to do that. But this is a good illustration of how these stresses, these shear stresses, are, and these normal stresses are going to be symmetric. Of note, I should have mentioned this earlier. If you wanted to measure if you wanted to measure the shear stress of your foot slipping on the floor, and you had a wonderful sensor that measured force, right, in the direction you're slipping, that would be one way to approximate the shear stress. Because what you've got is you've got some area of your foot, or your shoe, whatever it is, and if you measure the force of the area, right, the force is parallel to, well, force is actually perpendicular to the vector coming out of that area, but it's essentially sliding along that area. That would be the shear stress. Okay. After you take this expression for linear momentum, and we combine it with our conservation of mass, we can get the Navier-Stokes equations. Okay? And so what we would do is we would break this down into its three directions. Okay? And so what that looks like, okay, is going to be the Navier-Stokes. Let's see if we can do it. So in the x direction, we're going to have a rho and a g term. All right, so maybe there's grabbing x. Usually we just think of it as a z, but we could have a rho gx. We have a gradient of pressure, so in the x direction we can say it's just the derivative of the pressure in x, and it's minus. And then here we have the Laplacian, okay, of the velocity times the viscosity, so we can say we have plus. Right? And we have the Laplacian, so we're going to take the second derivative of what? We're taking, well, we have the velocity vector, so we're going to have the second derivative of u, okay, with respect to x, the second derivative of v with respect to x, and the second derivative of w with respect to x. Okay. And then we have the inertia term on the right. So this is rho dv dt, so it'll be rho du dt, like that. Okay. We can repeat this very briefly. But not repeat exactly, because we have to change some variables. Appropriately. Can't seem to do it. And then the same thing for z. Okay. And what was your general mode of operation for being able to solve problems in your fluid mechanics course? You wrote down Navier-Stokes equations, and then what did you do? Try? Yes. Okay, what? Scream. Okay, sorry. That sounds painful. So what did you do? You had a procedure, right? Yes, Jonathan.
You determine all the like initial conditions that you have, so you can take out some parts of it.
Right. So often if you're solving a steady state problem, we're hoping, not always, but often we were, but not always. So you would take a look at that kind of condition, right? And that would mean that your time terms go away. Not always though, okay? Especially if you got like a rust or something. And then you would also take a look at your boundary conditions. Like that's your kind of initial conditions, and sometimes yes, but often more the boundary. So this is where you say, oh, I have no slip on this wall, right? And that means that, okay, that's what's going to be occurring. Or I have no velocity in this direction, right? And so you just go through and you just cross, right? You cross out the various terms. Good. Oh man, I'm just, no one's correcting me, guys. And I am on a good one today. Okay, so this is going to be and this is going to be okay, like that. Okay, that makes everything better. Okay. So I'm sorry, no one's correcting me and I'm making mistakes. That's not a good comment. We're going to talk about the finite volume. Okay. Now, ANSYS Fluent uses the finite volume method, and many commercial packages use the finite volume. You can also talk a little bit about what people say about the finite element method versus the finite volume method. Okay, but this is the method that's happening underneath the hood as you work your problems. It might not be bad to take a little bit of a overview of how these methods work that we've been covering. So whether we're doing particle dynamics, or the heat equation, or fluid flow, we are discretizing the problem in this class, right? That's one of the main themes. And so you have a physical domain and you have phenomena. Okay? And we have to come up with a set of governing equations to handle the physics, and then we do some discretization. In these types of problems, we're now discretizing our geometry and our time. Okay? And you come up with a system of algebraic equations, and that has the general form of some kt is equal to a forcing function, like you see there. And then we take the inverse of k times that forcing function to get our column vector for, say, temperature, or whatever the values of interest might be. I think I need to take a moment and I need to close this because I'm having troubles. And hopefully it will save. Let me see. Actually, I'm going to do a save as. It's going to be dangerous. Like that. Okay, let's see. Is it going to let me write better? Yeah, it is. Okay, great. Okay, so in the discretization, what we've highlighted is that you have your domains, physical domains. You have your physical modeling, which comes in the way of, say, a heat equation, which is what we're going to be using. Heat equation, right? Fourier's law, flux, that's a flow. Okay, and so what we've got here is a way to represent that in the problems we're going to be solving. So we discretize our domain, we have our equations, and then once again we have our kt m equals f, and we're trying to figure out what the result is, right? So here, in the steady state situation, what we said, and before we said, so we were using Q before, all right? And in this case, Q dot, so Q dot or Q are, it's not the greatest, but they're interchangeable. Okay. And we're going to look at how we map this method to the heat equation. Remember, we've already done this a couple of times. We did it with finite difference, and we did it with the finite element. Now we're going to use the finite volume method. Okay, so the equation that we care about is the heat equation. Okay. And today we're going to use Q dot just to be well, consistent with what we have here. In the past, we just used Q. We talked previously about the conservation of mass and conservation of volume. So what's going to happen is we're going to look at this element number 9, okay, and we're going to look at the conservation of mass, or conservation of flow, or conservation of volume of flow in and out of this. Okay, so we can say that for our element 9, okay, and this is going to be for, essentially everything. We can think of it as having a control volume. And write it in this form with the physics. And we can also integrate the other side. Okay, so all we did is we took this equation for the physics, the heat equation, and we've integrated both sides. Now, we can then use the divergence theorem on the left side. Okay? The divergence theorem says that we can take this volume integral of a gradient and change it into a surface interval. So what it ends up looking like is this relationship. And on the right side, we just take the integral. So it's a volume integral on this small element, TV. So this just ends up being the heat flux in that element, and that control volume, times the volume of that element. And then we take the surface integral, so this is a surface integral, and we discretize this so that it's really just a summation of these k gradient t's times the surface area. Now you're like, what are you talking about? Okay, what we're talking about is for this element number 9, which is right here, which has now got its name C, element C, we're going to be looking at how volume, or how liquid, or how heat is flowing into or out of this element. Where can it flow to? Or what can it flow through? It flows through the wall. Okay? So what it doesn't flow to in this form, it doesn't flow to this element over here. Okay? It doesn't go through this corner. 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 I mean, it does ultimately communicate, because if you start here, right, then there's flux through these walls. Okay? But the way that this finite volume method works, it only goes through neighboring surfaces. So these surrounding surfaces are going to be lowercase f1, lowercase f2, lowercase f3, and lowercase f4. Now, what does that look like? It looks a little bit ugly, but not too bad. All right. First, let's think about what the areas of these are. Okay, so you see that there's this S sub F1, okay, and there's this S sub F2, there's this S sub F3. So we can say that here, okay, so this S F1 can be thought of as this length. All right, and yes, this is kind of a 2D problem. It is a 2D problem. Okay? So it would have some depth, but we're going to ignore that, and we're just going to say that this area is going to be this distance. Okay, so we could write that as, what is the delta y on this face 1? So that's this lowercase like that. And we can assign a vector to it, okay? We've done this before. And so it's going to be in the I hat direction. S subscript F2 is going to have a delta x, right? That's the area that we have here. So this is going to be a delta x on the face 2. And this is going to be in the y direction, the vertical direction. SF3, you can get how this is going. It's going in the negative direction, this vector is. And so it's going to be minus, and then the delta y on that third face, in the I direction, and SF4 is going to be in the minus X direction. Like that. Okay? So those are the surfaces. As a reminder, okay, the equation that we're trying to solve is going to be, well, it's this one right here. Okay? And this has the form of this comes from the divergence theorem and discretization of the divergence theorem. And now we'll attach some indices. So this is going to be on faces 1 through 4. This is on each face. And this is that SF. Okay. So what we actually can do with this equation, and now that we know what these SFs are, is we can say that the Riemann sum, okay, on these 4 surfaces is going to be the following. It's the physics. It'd be nice to have this. Okay. Yes. It's the minus k times the gradient of the temperature on this first face, dotted with SF1, okay, plus the minus k gradient of temperature on surface 2, on the second face, times the second surface area, plus minus k delta t on the third face, times SF3, plus minus k time over the fourth one, and this whole thing has to be equal to this q dot CVC. So it's kind of like conservation of volume, although it's kind of more like conservation of physics going through surfaces. Okay. How do you represent this gradient of temperature in a discretized world? What do you think? If we're discretizing a gradient, and it happens to be a gradient in a single direction, and it's discretized, what does it remind you of? How did we discretize derivatives a long time ago? We use by difference. So, what we can do is we can say that, well, let's do this. We can say that a discretized form of delta t would be to essentially make sure that we remember that this is essentially dt, either dx or dy, because it's going to be just in either x direction or the y direction. And we can say that we have now, as an example, the ability to look at a difference in temperature over a difference distance. Okay, so in this particular case, on face 1 over here, okay, what we're doing is we're saying, what's the temperature at the centroid of this neighboring element? What's the temperature at C? Okay, the centroid of the current element. So that's TF1 minus TC. And what's the difference in the distance? Over what distance is that happening? And that's how we say the gradient of temperature can be represented as this finite difference. And that's what we plug in to this set of equations. You would continue this on all the other faces, and you set up essentially a number of systems of equations, right? You're going to have one, this is one set of equations, this would be one row of your K matrix for this element in the whole model. Then if you go to this element, say F2, you have another row in your K matrix. Each one of these is going to be a separate row in your matrices. In the end, you're going to have the computer solve the problem of inverting this K matrix, okay? And you're going to once again be able to figure out what the distribution of temperature is. Okay? That is how the finite volume method works. Which one of these? Okay. If you had to choose to do the math for the finite element model or the finite volume model, finite element method or the finite volume method, which do you think has a simpler set of mathematical steps to get a K matrix? Do you remember? Recall, what did we have to do in the finite element method? Okay, well, we had to get a K matrix. We had the opportunity to, remember, we had to create these trial and test functions, right? These basis functions. We had to use the Galerkin method. We had a weak form. We had strong statements, and then we had weak statements. Okay, it's extremely complicated to do finite element. Okay, or it's more complicated to do finite element. This method is actually pretty straightforward. Now, there are some tricks that we don't talk about in terms of how you solve this matrix, this K matrix, or how you convert this K matrix efficiently, right? But what the computer essentially has to do is it has to discretize. So it keeps changing the size of the K matrix. Okay? Because if you can get away, if you have enough accuracy with few elements, right, then you have a certain K matrix. So when you're watching ANSYS solve these problems, you're going to see these things called residuals happen. Okay? And what's happening in those residuals? Those residuals are essentially ANSYS saying, oh, my K matrix was this size. Oh, that was not good enough because I'm not conserving volume, or I'm not conserving the quantities like I should be. It's using the finite volume method in fluid. I've got to increase the size of the K matrix. I've got to try more. I've got to discretize with smaller values. Then I figure out my residual is. It does all of this extremely quickly, and it's just plotting a nice little line that goes. Because what's happening, it's expanding the K matrix, and then it's trying to make a small K matrix, and it's expanding it until it gets convergence. Convergence. Okay. Here's just a bit on the finite volume method. It uses surface intervals, uses the divergence theorem, which we talked about. It looks at flux, it looks at conservation of flux, and the finite volume bit refers to the small volume surrounding each node point on a mesh. Okay, so you're still using meshes, and you're looking at these very small volumes. We could have called it finite element, but that would have been confusing, right? Okay, or we could have vice versa. They could have been flipped, but that's just how they've been named. Okay. As we've discussed, for CFD, ANSYS uses finite volume method. COMSOL does not. COMSOL uses the finite element method. All right, and if you read these blogs and various things, they will say anything you can do in finite volume method, I can do in finite element method. But they do point out that there are some times where you might want to use finite difference even, or finite volume, and these are those cases, right? So finite element method can do anything, but finite difference method could be appropriate for these types of situations. Weather, okay? Graphics, okay? Finite volume is really good for CFD or heat transfer, or is acceptable for heat transfer, okay? Because you can see here that heat transfer is up here and CFD is also there, right? They are very heavily committed to the finite element method, COMSOL is. And ANSYS, what do? They buy a company that does something well, and they put it in their packages, okay? And then we get to figure out how to make them all work together. All right, so today we reviewed some fluid mechanics. All right, we actually reviewed how to do outlines, paper outlines. We discussed some aspects of fluid mechanics, and then we discussed the finite volume method. And you'll get to use ANSYS on Fluent and have your first experiences with the finite volume method. At least when you go in for an interview, you can say, yeah, I use Fluent, and yeah, we could use the finite volume method. All right, so instead of saying, oh yeah, I use Fluent, I use the finite element method, you'll know that it's actually not that. All right, we'll go ahead and take the attendance. And let me stop.